welcome everyone. Happy to see you all here. So the reason why we decided to put this event together for today is because a group of engineers at Streamr have recently co-authored a white paper on the scalability of the Streamr peer-to-peer network with really cool results. So that's why, first of all, Streamr's co-founder and CEO, Henri Pihkala, will present the findings of this research. And after that, I invite you to stay around for a panel discussion on the evolution of peer-to-peer networks, all the way from BitTorrent to today's modern blockchains and peer-to-peer networks. And for that, we have invited a group of experts with backgrounds in decentralized networks. So that's going to be really interesting as well. And after that, we're going to have a Q&A. So if you have any questions on the network or if you have questions to the panelists, then just please wait until the end to ask your questions. Yeah, that's it for me. Now I would like to give the floor to Henri.
Okay, excellent. Let me just figure out the screen sharing here. This one, I think. Yep. Can you guys see the big screen?
Yes.
Just a sec. Let me get rid of the Zoom webinar chat window still. Yep. Okay. Okay, all good to go. All right. So, yeah, welcome everyone. I'm Henri, co-founder of the Streamr project. This session is about the Streamr network, or to be more precise, the research we've done over the past year or so on the scalability and performance of the Streamr network. This talk will be pretty technical, although the motivations for the research as well as the key results should be quite easy to follow for everyone. So we've published the research in the form of an academic paper available at streamr.network/network-whitepaper. There's also an easy to read blog post that just presents the key results. And this presentation will be sort of closer to the blog post in terms of how deep we're going to go. And we should be done in around 30 minutes. So here's what we're going to do. Not all of you might know what the Streamr network is, so I'll briefly explain it to kick things off. Then we'll look at the intended use cases and requirements for the Streamr network and discuss some of the design choices we made based on those, which will finally bring us to the real-world experiments and their results. So there will be Q&A in the very end, like Marlene said, meaning after the presentation and the panel. So you might want to write down any questions that come to mind. So let's jump into it. So first of all, what is the Streamr network? So here we have a data source called a publisher. It could be a mobile phone, an IoT device, an application running on your laptop, anything that generates some sort of events that we need to transport to listeners elsewhere, called subscribers. And traditionally, this is done with a centralized message broker, a server that all parties connect to. So the publisher publishes a data point to the server, and the server forwards it to all subscribers interested in that data. And this is how real-time data flows between multiple stakeholders or multiple applications work today. Now, however, this is obviously not scalable, as all data needs to pass through this broker. It's also not very robust, as there's a single point of failure. It's not private, as the central point often sees what data is being exchanged and who are communicating, and not open. I mean, whoever runs this central service decides who can use it and sets the pricing and so on. And finally, it's not connected. Such data pipelines can't talk to other data pipelines, creating silos and making interconnectivity impossible. So in the Streamr network, there is no central data broker. Instead, a peer-to-peer network is formed where all publishers and all subscribers act as brokers, sort of, and relay data to each other in a mesh called a topology. Now, this is a peer-to-peer approach that has the opportunity to solve the problems of centralized solutions. However, building a good system that actually solves them is a bit tricky, because there are a lot of decisions to be made about how exactly the peers connect to each other and propagate messages. And evaluating the different approaches isn't easy either, because the differences only start to appear at large scale. So to be able to make the appropriate design choices, we need to specify the requirements for the network, and requirements follow from the intended use cases for the network. So the Streamr network targets machine data flows, such as those coming from IoT or other telemetrics use cases, with typically frequent, quite small message payloads containing the latest sensor readings and whatnot. On the other hand, environments like smart cities, where multiple stakeholders are publishing data, sometimes it's open data to be used by the general public. Smart traffic environments, where you could have millions of devices producing latency sensitive information, such as warnings about accidents or potholes. Or data crowdsourcing, where a large number of individuals are sharing the data streams they produce, such as metrics about the websites they visit or apps they use. Of course, the tech isn't limited to just these examples, but they act as an inspiration and start to sort of outline a problem space that we want to work on. So let's look at the requirements set by the intended use cases. The white paper lists 11 requirements, but I'm going to just highlight some of them here. First of all comes scalability. So the goal is to make a protocol that can act as this global data fabric capable of handling large numbers of participants and large volumes of data. Decentralization. The system shouldn't have any single points of failure, not technical ones, and not operational ones. All parties need to be able to interact with the network regardless of each other without anyone's permission. And for example, someone leaving or failing to operate correctly shouldn't affect the quality of service for others. And third, we should have low and predictable latency, as well as guarantees about message delivery. So every connected subscriber should receive every message in a low and predictable time frame. For example, a traffic warning system would be pretty bad if it took minutes to propagate the information to every car in a particular area, or if the subscribers got a particular warning with only, say, 95% probability, right? The network should have good churn tolerance, which means that the network should continue to offer a good quality of service, even if nodes continuously join and leave the network. And finally, the message size in the intended use cases tends to be quite small, typically smaller than a few kilobytes. So this characteristic should be taken into account. So in the paper, we explain how our design choices aim to address each requirement, but in the actual experiments, we focused especially on two of these requirements, the scalability and the latency characteristics of the network. Now, those are very relevant for many use cases, and they are ones that can't really be, confidently theoreticized about. So they need to be tried out in the real world. So what does scalability mean anyway? From our perspective, there are three main dimensions where the network needs to keep delivering good performance when some or all of them grow large. First, there's the number of streams. Now, in order for this to be this open connective tissue between numerous different systems, the network needs to be able to handle any number of different data streams from different publishers. And second, it should be able to handle very large volumes of data in those individual streams, right? And finally, it should behave well when the number of nodes, meaning the size of the message passing topology, grows large. For example, when there's a large amount of subscribers for a given stream. In the Streamr network, 2 of these 3 dimensions have straightforward scaling solutions, while one of them doesn't have an easy answer. I'll pause for a second. Try and guess which one is the hard one. So scalability on the number of streams axis can be easily achieved by having independent topologies for each stream. You see, scalability would be limited by some scarce resource that different streams need to share and compete over. But by making each stream independent, there is no resource that would be both shared and scarce. So more streams can be supported by simply adding more nodes, basically. Now, a large amount of data could overwhelm nodes while trying to handle it. This can be solved via sharding, also known as partitioning, which means just splitting that large stream to multiple smaller ones. Imagine that the data flow is a large river that at one point gets split into multiple smaller brooks, right? Now the total amount of water flowing through the small brooks equals the flow of the big river, but swimming in the big river might drown you, while swimming in any of the brooks is safe. So this bit sort of maps back to the number of streams problem, which we already solved with the independent topologies. However, there's no easy answer to address the scalability in terms of the size of the topology. It depends heavily on the structure of the topology and how the message passing works within the topology. And therefore, this dimension has been the main focus of our scalability research. So first we need to choose what type of topologies we want to construct to achieve the requirements like scalability, low latency, and churn tolerance. In the Streamr network, we've chosen deregular random graphs. Now, that's a bit of a mouthful, so let's break that down. A regular graph simply means that every node has the same number of connections to other nodes. And that number is set by the parameter d, called the node degree. Random here means that the d neighbor nodes are chosen randomly. So the topologies end up looking a little bit like this, like the little dust balls that I find on my floor when I haven't vacuumed in a while. This class of topologies is interesting because their properties are well known in the academic literature, and they are actually much better than you might intuitively expect, as we're going to soon see. Another attractive thing is that they are super simple. There's just one parameter, the node degree, d. So we need to select a good value for the node degree d. So let's look at what effects it has on the topology when the number of nodes in the topology grows large. One interesting metric to look at is network diameter. That's the maximum number of hops you'd ever need to travel to get from any one node in the network to any other node in the network. Now, existing literature about regular random graphs tells us how the network diameter behaves as a function of the node degree d and the number of nodes. From the image, we can see that the diameter grows logarithmically with the number of nodes. And logarithmically means very slowly. So this is very promising. From the plot, we can see that even in a huge topology of 100,000 nodes, even the most distant nodes can communicate with only 15 hops if every node has 4 neighbors, or with around 10 hops if every node has 6 neighbors. Now, reasoning about the node degree a bit more, let's intersect the graph here at 100,000 nodes and plot just those diameters. Here we can see there's diminishing returns. Growing the node degree brings smaller and smaller improvements to the network diameter. Let's compare that with another metric here called message redundancy. Now, redundancy means the number of duplicate messages received by each node. And redundancy is both good and bad, right? More redundancy improves churn tolerance and protects against censorship attacks, for example. But on the other hand, it wastes bandwidth. And in the Streamr network, we're using a simple message propagation model called flooding, where every node propagates messages to basically all its neighbors, except the one that it got it from. The good thing about this model is that it guarantees message delivery, which we want. But on the other hand, the message redundancy grows linearly with node degree. So the node degree controls an important trade-off of network diameter versus bandwidth consumption due to this redundancy. And since we have diminishing returns on the diameter, while we have linearly increasing penalties on the bandwidth consumption, the smaller end of values like 4 or 6 make most sense for our use cases, offering a good balance. Now we should note here that network diameter, which is measured in hops, isn't the same as latency. In the real world, the latency for each hop or each connection between peers will vary greatly depending on what nodes happen to be in question, where they are physically located, and what kind of internet connection they have. So that's why we conducted real-world experiments at scale to see how latency actually behaves, hoping that it would behave logarithmically, like the network diameter. So we've basically chosen the node degree 4 to conduct these real-world experiments with, and we've also set that to be the default value in the Streamr network. And it should be noted that since the topologies of different streams are independent in the Streamr network, each stream could have a different selection of D depending on the use case, allowing the stream owner to tweak this trade-off to their liking. So we wanted to find out if latency scales logarithmically and also measure the absolute latencies to get an idea of how long it takes to propagate messages over the Streamr network. A fair question, right? So we selected 16 different AWS data centers around the world. We ran from 2 to 128 virtual machines in each of these 16 regions, giving us network topologies of 32 to up to 2048 nodes. Now, with the clocks of each machine carefully synchronized, each node took turns publishing messages containing a timestamp. And when the other nodes received those messages, they logged the latency by looking at how old the message was. And because the topologies are random, we did 10 repetitions for each network size to see the average results, as well as get a glimpse of how the different topologies of the same size perform relative to each other. And here's one of the key results from the experiment. Many of you have seen this as it was in the invitation email for this event, I believe. So this image is a cumulative density function of all the observed latencies across all the repetitions, with each network size drawn as a separate line. Now the y-axis runs from 0 to 1, meaning 0 to 100% of the broadcasted messages. Now from this image we can read things like in a 32 nodes network, which is the blue line, 20% of the messages were received in, let's say, under 90 milliseconds. 50% were received in around, let's say, 150 milliseconds, and all of them in maybe 250 milliseconds. In a 2048 nodes network, which is the as the main competitors for basically any decentralized system are, of course, the centralized services that do similar things. Here are the selling points of PubNub, a popular cloud service for publish, subscribe, or PubSub message brokering. So doing the exact same thing. So to put our numbers in context, in their marketing material, they promise 1/4 of a second latency worldwide, which is 250 milliseconds, which is in the same ballpark than we just saw on the Streamr network. The big boys are less eager to market their performance metrics. For example, the Google Cloud PubSub service doesn't give any such promises, and actual long tails of several seconds have been reported by users. But anyway, it's interesting to see that even with the relatively simple choices for topology construction and message propagation, the Streamr protocol already has the performance needed to basically replace these popular centralized services, which means users can get all the benefits of decentralization, getting to use an open, permissionless, and trustless system with no downsides at all, not even a latency hit, which would be the primary suspect in any peer-to-peer network, really. If we plot the measured latencies as a function of the number of nodes, this is what we would get. So the thick line here is the average latency across all repetitions for each network size. The topologies are random, so some topologies will just be faster than others by chance. And the shaded area here shows the difference in average latency between the fastest and slowest topology out of those 10 repeats for each network size. So in this graph, we see two important things. First of all, we do see the logarithmic scalability, which verifies our hypothesis that the latency behaves very well at scale. And secondly, we can get a feel for how much room there is for optimization, shown by the shaded area. So basically, here we can see that with 2048 nodes, the average topology delivered an average latency of a bit over 190 milliseconds, while the best topology delivered an average latency around 180 milliseconds. So in general, we saw a difference in the range of 5 to 13% compared to the average topology. So not that much. This is the rough ballpark of what you might be able to gain by creating some smarter than random topologies. So these are actually, the random ones are actually pretty good. Here's a graph that's similar, but not the same, where the measured latencies were divided by the ping time between the publisher and the receiving node. So the ping time, the direct route on the internet, is obviously the fastest one achievable. And that latency divided by itself would get a score of 1 on the y-axis here. So the peer-to-peer routing with its multiple hops can, of course, only add latency. But on the other hand, you can't have everyone connect directly to the source, as that would be unscalable and insecure. So even though it's impractical, the direct latency is a useful measuring stick. And we can see that the peer-to-peer network operates at a multiplier of around 2 to 3 times the direct latency, which is, again, pretty good. The vast majority of use cases, they should trade a little bit of latency for scalability, security, and new business opportunities. It doesn't matter if the latency is 25 or 75 milliseconds. The only use cases where that might make a difference are things like, fast-paced online games or high-frequency arbitrage trading or stuff like that. And for those things, some tailor-made data pipeline is the way to go. The last chart, I promise. So we also tried whether it would be possible to predict the latencies before sending any messages to the network by having knowledge of the latencies of individual links between neighboring nodes. And it turns out that these estimates are accurate with an error of only around 3 to 5%. So the estimate computed from the node-to-node latencies is effectively a lower bound, with the overhead coming from message processing delays at each hop, which we ignored in the estimation. So wrapping things up, we've looked at the topologies in the Streamr network and how they behave and scale with a large number of participating nodes, and found that latencies scale logarithmically with topology size. The maximum latencies of around 150 to 350 milliseconds can be expected in a global real-world setting. The random graphs perform actually pretty well out of the box, with only limited gains achievable by trying to construct smarter topologies. This is, of course, in the space of regular graphs. Irregular graphs would be a whole different kind of worms to open. And finally, the performance of the decentralized network is already roughly on par with centralized cloud solutions that provide a similar message brokering service. So this means that users will have little reason to use centralized services in the future, as decentralization liberates them from vendor lock-in, improves the security and robustness of their data flows, while also opening the door to global data economies, data sharing, and data monetization. Okay, that's pretty much our findings in a nutshell. If you want to go deeper, I recommend checking out the paper itself. Yeah, thanks everyone for listening, and I'm handing over to our host, Marlene. Thanks.
Thank you very much for this, Henry. That was really interesting, I think, for a lot of us. So yeah, if any of you has any questions, as said, we're going to do the Q&A after the panel. And now I would like to hand over to María Paula, who's going to be the host of our panel. Thank you very much for chairing the panel, María.
Hey, hello everyone. I'm María Paula. I am in crypto since 2017 when I joined the Web3 Foundation as employee number 3. And I've been at Golem for 2.5 years now. I'm super excited about the future of Golem. We're building a completely new platform right now. We just launched after 2 years on the mainnet. And we have been friends with Streamr for a very long time as well. I'm really happy about the panelists as well. They're all really awesome. So yeah, that's my intro, and probably we wanna do some round of intros. Maybe Fatemeh, would you like to start?
Thank you, Maria. And thank you, Henry, for the interesting talk. It was very, very nice. Great job. Thanks first for inviting me. I am not so long as you, Maria, in the blockchain space, a bit less. I joined in 2018 as a researcher at Web3 Foundation, and started to be interested in networking topics there, but also interoperability. Last year, I started the role as research team lead to help out also for driving the research agenda at the Web3 Foundation and trying to support the research team. And now for the last month, or like September, I have also taken the role as interim CTO in Web3 Foundation. Right now, in the last, I would say, couple of months, I have done a bit less research, but I think most of my research personally was interoperability. In terms of networking, we have an excellent networking engineer who does interesting work for us, but I can go into that a bit later after the round of introductions.
Great. Sebastian, do you want to introduce yourself?
Sure. Thank you, Maria, for hosting this. Yeah, so my name is Sebastian. I'm founder of HOPR. It's a layer 0 privacy foundation for the Web3. And yeah, we are early on working with a bunch of people here, have been neighbors pretty much with Henry and Fatemeh in Zug. Now we're based in Zurich, which for the international people is like 20 minutes away, which is very, very far in Switzerland.
Cool. Karissa?
Hi, can you hear me all right? My name is Karissa, and I am a maintainer at Decentralization Off the Shelf. I've been working on peer-to-peer systems since 2014. I was number 3 at the DAT project, and I am an engineer by training, but in the past few years, I've been focusing more on how architecture impacts user experience.
Cool. Henry, I guess that you introduced yourself. Anything that you want to add?
Yeah, I mean, I'm an engineer by heart, but CEO by day. So I sort of do a dual role in the Streamr project. Yeah, I'm based in Zug, like Sebastian already mentioned. So I guess that's pretty much it for me.
Right, cool. So let's get to the panel then. I prepared some questions. Basically, we have a little bit of, we don't have much time, so I prepared one question for each panelist, and then we're going to have a closing question, and then you guys in the audience can ask any questions that you want as well in an open fashion. So I'm going to start with Fatemeh. I'm really impressed with all that the foundation and Polkadot has achieved. I started with the sale, so this is all really amazing. I'm participating of the network as well, both Kusama and Polkadot. So I've noticed that the research arm of the foundation has been complementing really well the development of the Polkadot network. And I wanted to ask you, which of the projects that you help with is the one that's going to be essential within, you know, the future of P2P?
Thank you, Maria. In terms of helping out, I think I have, I don't do the most of the networking research is not done hands-on by me. So I do a lot of driving of the agenda. We have, as I said already, a team of researchers. I think currently we have 9 researchers. In terms of networking, Polkadot has very specific needs that are unique to its nature, to the structure of Polkadot. In the recent years, it had the peer-to-peer use in blockchain space has been very interesting, and I think blockchain technologies have been a huge driver of the peer-to-peer technologies. However, for Polkadot, because we do have a hierarchical structure, there are more security requirements. For example, for us, networking has to be very reliable, while, for example, in a lot of other systems, that reliability is not as necessary as in Polkadot. Like when if a message is sent, we have to make sure that within a very short time that message is arrived. And also the amount of data that is sent around is going to be quite large. So both in terms of security and in terms of efficiency, we had quite a number of challenges for networking. Now, networking has been a part of all of our sub-protocols. So we don't have any single sub-protocol that I could tell you, this is the part that, is the strong networking part. Networking is relevant for all of them. And each one of them have different security needs and different challenges in terms of how much data is sent out or how much delay they can tolerate. But I would not be able to tell which one of the parts of Polkadot or Kusama would be more, strong in terms of driving the peer-to-peer technologies. But I do believe that a lot of the efforts that we are doing, especially in terms of security and reliability, hopefully will be useful to other projects too. Everything that we do in the research team at Web3 Foundation is public, and also the codes that we are producing is open. So we always have that in mind and hope that we can be a driver of improving this great field.
Definitely, judging by the advancements that you guys have achieved and everything, I think it's worth taking a look at the entire project and taking a look at the documentation, which I need to do myself as well. So thank you so much. So let's move on to Sebastian. Actually, when I first contributed to the Whisper, to the HOPR Gitcoin grant, it was just the next generation Whisper, and all of a sudden you decided to sort of pivot, but in a really amazing way, to a full layer 0 solution. The contribution that the project has done to the advancement of privacy preserving technologies is just great. So what are the next steps for you, Sebastian, and for HOPR, and which is for you the end game of the protocol?
Cool, thanks for that. And thanks first of all for helping out early on. Gitcoin has been tremendously helpful to HOPR and many other early stage projects. So firstly, I think we've been in this weird discovery stage of what you're actually doing, and that's very important to acknowledge. When people talk about messaging in English, it's kind of weird, right? Because when we talk about messaging to the status people, they were always thinking about chat, right? When you talk about messaging to the Whisper people, they're thinking a lot about broadcast. But what we realized, what isn't really there, is really a basis for point-to-point communication that you can use for any sort of application. It could be chat, it could be broadcasting your Ethereum transactions, it could be any sort of like point-to-point interaction that we have out there. And what we specifically focus on is privacy. So for us, I would say Streamr is very much focused on efficiency and getting data across like in a fast way, in a like minimal latency way. What at HOPR we're focusing on is privacy, right? So no third party should know what's going on. So so currently we have our first incentivized testnet. It's still a little bit rough around the edges, so it's a bit wild, but that's good. And for me, really, you asked me a bit about the end game. I mean, that's tough, but I hope that we will live in a world that's truly decentralized, that we have less single points of failure, that we have less single points of control, and even more importantly, maybe abuse of that control, right? And what that means is that we need means of communication and exchanging data that are privacy preserving, that should not be abusable by not just governments, really. We think about a lot of times about governments, but I'm at least as concerned about private for-profit corporations that want to kind of choke data exchange highways that our modern world needs. And this is really what we built HOPR for.
Great. Which stage are you with HOPR right now, and what's the best way to find your resources?
Yeah, so basically you can either go on hoppernet.org, HOPR, hoppernet.org, or hoppernet on Telegram. We have an incentivized testnet that we've launched on the XDAI chain about 2 weeks ago. You can run a node and you can, yeah, if you're lucky, earn some tokens for keeping your node up and running and relaying currently relatively pointless traffic, but I hope we'll change that soon when we approach mainnet towards the end of this year. So that's a bit the roadmap.
Great, thank you so much. I'm really looking forward, by the way. So let's move on to Karissa. You research all the hairy topics on P2P adoption and design. That's obviously security, resilience, and usability. Obviously, there is a very big problem in the world of decentralized technologies and P2P technologies on achieving a good balance in this trilemma. And I personally believe that we're a little bit far, but maybe you can prove me wrong as well. My question is, which are the challenges, which are your main takeaways, from the research that you have already done, and how do you approach these as Simply Secure?
Yeah, I think you're right about the trilemma being quite difficult to overcome. I mean, one of the missing aspects we've seen are tools that developers and designers can use. And I don't just mean physical tools or technical tools, but mental models, project management skills, communication skills, these kinds of things that people can use to understand how to build applications. So we're producing a library of resources, assets, and patterns to support the design and development of better user-facing applications that are backed by decentralized architecture. And our key finding is that there is a significant gap between the decentralized protocols that we're all creating and the application that users actually can and want to adopt. I really like, and I hear a lot that people are focusing on particular use cases, which is really great. I think that's a really good first step to figuring out which trade-offs are good and communicating those trade-offs. And I really like that all the panelists here and Streamr itself, really focus on, like, there are all these things we could do, but let's just focus on something that, we're going to be really explicit about what we're going to focus on. I think that's a really good first step to building a protocol that you can actually find actual users for. And I think that building in design of the architecture as well as end user designers into the process early is super, super important. So what we've been looking at are patterns across the ecosystem of applications and protocols that we can use to drive the development of the centralized protocols. So when we talk about a design pattern, we're talking about something that people are potentially doing over and over again, and people are sort of reinventing the wheel. There are certain patterns that people expect in centralized systems that they cannot expect anymore in a decentralized system. So one of these is, for example, who else knows who I am? Can I be anonymous? So, like, as Streamr showed in the broker model, you have to trust a particular broker, right? And this is a bad thing for a variety of reasons, but it also is a good thing because it has transparency around, like, oh, this broker, I'm trusting this broker. I know that this broker knows who I am, but maybe that's the only company that knows who I am. So maybe they decide they trust that company. I don't, but maybe some people do. I think that there's a lot we need to think about in terms of privacy. Just because something is decentralized and peer-to-peer doesn't mean that it's safe for users or that it's private for users. So we have to think about that and how we communicate that to end users. I think there's a lot missing there. But I think that we're going to get there eventually. We just need to figure out, what's best and how to move forward. And I think it's a particularly important in the next 10 years because we see a huge increased interest in decentralized technology as a response to surveillance capitalism, to security breaches, and monopolization of technologies. But there are actually very few projects that offer the security and the service that end users are looking for from an alternative. So threats to privacy and safety really need to be understood by system designers, application developers, as well as end users. And just one point we talk about as well in the paper, there's a paper you can read at decentpatterns.xyz, is DECENTPATTERNS at XYZ. We also talk about blockchain and how people talk about blockchain as trustless, but when an end user is actually using it, they're actually trusting a lot of people. They're trusting the client developers, they're trusting the protocol developers, they're trusting the miners, they're trusting all these different people that work in harmony, and often end users are not involved in those conversations. So again, these rules that are set by developers, designers, investors, funders, and these roles might represent, and they often do represent, existing power imbalances that we see in technology today. So if you're going to include a blockchain as a primary component, you should also seriously consider like social, legal, and organizational and privacy issues when you do that. So these are the kinds of things that we talk about and we're working on. You can stay up to date with us. We have a mailing list. We also do consulting with protocols and projects to improve their safety and privacy and design concerns and help their applications get adoption.
Great. Interesting that you mentioned the trustless sort of dilemma. You know, I think it's a lot of marketing word, and actually in Spanish, for example, I'm a native Spanish speaker. Trustless, when you translate it directly, has a very negative connotation. And I think that as well, you spoke about rewiring the minds of users because they have a different user journey, and words should actually accompany all of that. So yeah, really interesting. I would like to ask everyone in the panel if you can just drop the links from your research, your GitHubs and everything in the chat window so that we can all keep track of them and our audience can discover them. So yeah, thank you so much, Karissa, and I'm really looking forward to check the paper as well. And I'm gonna move on to Henri. Of course, as we know, Streamr has been shipping and publishing continuously for the past year, a lot to catch up on. I haven't been able to catch up on the last paper, but I will. And the last white paper basically focuses on performance and scalability, as you said, but since you shared a fair bit on your talk, let's talk about your personal conclusion on how P2P has worked its way from basic file sharing to the current ecosystem. Do you have any takeaways? Sorry for that. And what we'd like to see in the next 5 years?
Yeah, okay. Well, I think the early history of peer-to-peer technology was sort of unfortunately characterized by a bit shady early adopters where, you know, the killer app for BitTorrent was basically sharing of copyrighted content, or one of the early use cases for Bitcoin was basically paying for illegal items and services. So obviously we've come a long way since then. And today there's a wide array of powerful use cases for peer-to-peer, ranging from the financial ones like, you know, ICOs and DeFi stuff, to the more infrastructure ones like data sharing, file storage, computation, with blockchain technology allowing us to add these incentive structures to make those peer-to-peer economies work. So we've entered this new era where the shadow of the early days has sort of passed, I hope, and the technologies are starting to be ready for serious use cases, for adoption in industries. And that's what I'd like to see happen in the next 5 years. Now, okay, many of the use cases depend on the on-chain scalability, for example, that we almost have now and will certainly have within 5 years. But if I can go beyond 5 years, let's say 10 years, I'm predicting a massive infrastructure shift from cloud services to decentralized services. It will be like the shift from private data centers to the cloud, but only bigger, because nowadays every company is an online company, right? So yeah, I don't know how long it will take exactly, but it will happen it will happen before we have man on Mars. Let's say that.
Hopefully. Really interesting. And if people are considering decentralized cloud, I hope they choose Golem, because that's where I work. But jokes aside, we don't have much time, but I really want to ask you the last question. What is, in your opinion, the most important event that has made the most impact in the evolution of P2P systems? So which one would it be, and why? Obviously, I'm gonna go for P2P money and Bitcoin, but maybe you can prove me wrong.
No, I'd actually definitely agree with that. By far, it must be blockchain, and more specifically, maybe proof of work, because for the first time, it allowed value to be transferred peer-to-peer. And like I mentioned, having that capability allows you to build these incentive mechanisms, which in turn allow you to build almost any kind of peer-to-peer infrastructures, which again leads all to the innovation that follows. So yeah, blockchain and proof of work would be
I would counter that to say the media sharing, or like BitTorrent and so on, they were the first boom from my point of view for real world usage of peer-to-peer. I mean, in university, everything was quite, the theory was there, but in real world, it was not a thing until BitTorrent and all of these famous media sharing things came around. What I do agree to is, though, because of the value that the blockchain systems had, security and efficiency became quite more important. In BitTorrent, people are willing to wait for 5 minutes to get a movie. But in the blockchain technologies, we know that we cannot wait 10 minutes for a block to be just delivered from one node to another node. And also the security just became quite more important. So I do agree that with you that in terms of security and efficiency, blockchain was the big driver. But the first baby step was maybe the media sharing applications like BitTorrent.
Sure. Karissa, what do you think?
Yeah, I think BitTorrent was big, but it also, and Napster as well. But I think there were lots of, security and privacy issues with those that caused actual harm to real people by just, downloading a movie or uploading one. So the consequences there are huge. I think also, I would also agree with Henri about P2P and Bitcoin and proof of work. And I think Bitcoin in particular, because it brought so much attention and promise of there's going to be a lot of money in this, like investors started coming along and then they started investing money into it. And I think that is the huge thing where now you have all these people who are getting trained up and engineers that are learning about the stuff and building it. Even if all of the projects fail, we'll have all this amazing knowledge that we've built and all this open source software. And I think that is going to last.
Yeah, for sure. And it's, Bitcoin is essentially, whether you like the community or the builders or not, it's the emancipation of money as well, which gives unprecedented freedom to any user. So yeah, I'm here with you, Henri and Karissa. What do you think, Sebastian?
Yeah, I think from a personal side, I would say Napster was for me definitely the first moment that I remember from my teenage years that I had to keep my computer up and running, I wasn't sitting there and my computer was downloading, let's say it was safe copies of my own data. It might have been somebody else's that it was downloading. So it was really my first interfacing a peer-to-peer network that has a global scale of doing something useful to me as a teenager downloading movies, right? And the second thing also was definitely Bitcoin, because it was the thing that led me to definitely massively pivot my career and look at, this crazy thing is not just for downloading movies, it actually has incentives, right? There's some random stranger somewhere on the planet that secures the infrastructure that I'm using to send money around. That's just insane. So, I would say it's super exciting times that we can see that. And yeah, let's all keep building that. That's just great.
May
what a great time to be alive.
Yeah, it is.
That we didn't make any family computer explode by using Napster or BitTorrent. So, so yeah, anyone has anything else that you want to share, or should we go to questions? Right, so thank you so much, everyone. This has been great and refreshing. Marlene, do you want to lead the questions?
Yeah, sure. I'm happy to do that. So if any one of you got questions in the audience to the panelists or to Henry on the white paper in particular, then feel free to just drop them in the chat. If you have longer questions, I can also give you panel rights, and then you can also speak if that's easier instead of typing them down. All right, I think we already have like the first question here. Henry, do you want to pick the first one, or?
No, go ahead. If you have sort of visibility into all questions, sure. Then
so the first question is, one of the panelists said Streamr focuses on efficiency while their network will be more focused on privacy. What is Henry's reaction on this?
Yeah, I think that's a great thing. I mean, I've known Sebastian for quite some time, and in this space, there's for sure a demand for different types of solutions. There, like you saw from my presentation, the choices that need to be made are always some sort of compromises. So you need to balance, you need to balance between latency or bandwidth consumption, for example. You might need to balance between how you handle your metadata and how easy your system is to onboard. Even from blockchain space, we know that you need to balance between creating strong consensus or getting scalability on a layer 2 thing, but you can't really have both at the same time. So I think diversity is excellent. There's demand for all kinds of solutions. While we focus on machine data, and of course there are privacy concerns within machine data, because sometimes it comes from applications that users are using, and it can be personal data and that kind of thing. Privacy-centric solutions are for sure something that complement the space. And I like what the HOPR guys are doing, and I've been following their work for a long time. So I also hope that there can be collaboration and exchange of ideas like there has been in the past as well.
Sebastian, you want to say anything about that as well?
Yeah, I mean, I agree very much. So it's many times there is this fundamental trade-off that Henry was summarizing. Basically, you can imagine if you have zero latency, you have zero privacy. And that kind of sucks, right? But I would say Streamr is definitely bringing the one end of the spectrum, and we bring the other end of the spectrum, which is the latency will kind of suck for, let's say, this video conversation over HOPR. It, depending on what privacy you would have there, it might just not work. So I can imagine that we will not just see these 2 points on the spectrum, but something in between. And in the end, everybody should choose, right? So some applications simply do not need privacy, whereas others do need a lot of privacy and are not so focused on efficiency.
Cool. The next question we had was, what streams do you think are not possible to do with existing data providers, but that could be done with Streamr, if any? For example, which streams would be too impractical or very expensive, or would break the terms and conditions of the centralized networks? Yeah, I think that one's for you, Henry.
Yeah, I think in general, the space where we have multiple stakeholders are tricky to do with current solutions. Like you can set up a data pipeline in the cloud or in your own data center or wherever, but it's not an open one. So managing permissions is difficult. You can't really do that at scale. If you're doing it in a consortium setting where there's 10 participants or whatever, it can still be set up manually and with paper contracts and that kind of things. But if you want to create this sort of dynamic ecosystem where the data is out there, it's available, and anyone can, for example, purchase access to it, then that is very hard to do with centralized solutions. Of course, there's now like centralized data marketplaces and that kind of things being built, and that will solve part of the problem, but it doesn't remove the fundamental problem of centralized systems, where the central thing is a single point of failure and sees all your data, which is exactly what we want to sort of move away from in the future. So the sort of scope of subscriber, or broad scope of subscribers is one thing, but there's the other side of things, which is the broad scope of publishers. So if you want to do something like data crowdsourcing, like let's say everyone who has, I don't know, Apple phone or whatever would be contributing data to some pool, right? Which is actually something that we're trying to enable with the data unions framework that we're working on right now. Then that kind of thing also becomes relatively difficult. Of course, application makers already today are, collecting data from their users, but that happens within the terms and conditions of those applications and sort of secretly from the user. So the user doesn't really own their data, for example. They don't get compensated for that data. So with peer-to-peer systems, all of that can change so that you can actually earn your data, and you can actually also sell your data as part of a bigger data product, which allows individuals to tap into these sort of permissionless and open data economies, which just don't exist in the centralized traditional world at all.
All right, we have another question for Fatemeh. What's the status on Polkadot's agnostic messaging?
We have implemented messaging for Polkadot, but we are constantly improving it. So I would say that we have had very good progress, and we are at a very good stage, but a lot of more exciting optimizations are also coming very shortly. So as soon as maybe 1 or 2 months.
All right, interesting. Yeah, Henri, we had another question for you on the network, which is the latency guaranteed by PubNub is below 250 milliseconds, whilst the goal is below 100 milliseconds. Does making guarantees and setting goals for the Streamr network make sense?
Yeah, maybe not setting guarantees. What we can show is the results and the sort of distribution that can be expected. Of course, there's tails on both ends, and it is a decentralized system. So I think making guarantees is easier in a centralized system because you can tweak every aspect of it, and you can sort of optimize those data flows, and there's some central party that sees all the data flows, like where it comes from and where it goes. So you can optimize that. Whereas in a decentralized network, this isn't really possible because there's no one who sort of controls the whole thing. But I think still, like, just putting the data out there makes it much easier for anyone who's considering to use a particular protocol or solution, much easier, because then they can see that, okay, my requirements are this, and these are the things that fulfill those requirements, and then that's that. And of course, the decentralized systems will get better and better over time. So I would be amazed if still, like I said, 10 years from now, if someone's still going to these centralized services, I will be amazed.
All right. Yeah, I think we have one last question here, which is, what is the scaling process of Streamr? So that's quite a general one.
Yeah, I wonder what scaling process means here from a technical point of view.
Up to you.
Yeah, I guess. So I guess I explained it from a technical point of view quite well in the paper. So there's basically 3 aspects. One is like how many streams there can be, and that's achieved by sort of creating this independence between the streams. And then there's the volume of data that reverts to the first one. And then there's this scalability over the topology size that was discussed in the paper. I think one more interesting, or not more interesting, but actually another sort of angle to scaling is how to, how to bring it to market and how to put it out there to people and how to decentralize. And that, of course, comes back to the sort of incentive mechanisms enabled by blockchains and cryptocurrency. So at the moment, we don't have an incentive layer yet on the Streamr network. But once we do, then people will be basically able to earn tokens by running those nodes. And that's how we can scale out the network. But that's actually not the only thing, because that's just an explicit incentive to run nodes in the network. But there are also implicit incentives. So for example, if somebody's using Streamr for a use case, let's say there's an enterprise and they have a use case for which they use Streamr, then they have an incentive to run nodes also in the network. Not because they want to earn rewards, but because they want their use case to be sort of safe from the point of view that if there's a nuclear war and everybody else stops running nodes, then their use case will still work. And that creates these sort of implicit incentives create another economic incentive to why people would run nodes in the Streamr network, enabling the whole network to sort of scale out in practice.
All right. We have one other question from Remy about if there is any update on the Network Explorer tool.
Somebody, Remy is paying a lot of attention. Yeah, we just started working on this new tool. It will be a public web app basically that allows you to inspect what's happening in the network. At the moment, the network is of course still small. There's only 8 nodes in the network, but once we start to decentralize, then this tool will allow people to see like where the nodes are, what's happening, which nodes are participating in which topology. And eventually, once we introduce the incentive layers, then the tool will also show like what each node is earning and that kind of things. So we're currently just started working on it. I'm not sure when exactly it will be ready, maybe towards the end of this year or early next one.
One other question we had from Oliver is when we can expect the first nodes run by the community.
For Streamr?
I would think so, yeah.
Yeah, I mean, we're quite close to that. Basically, we've promised that to happen only at the next milestone, which is Brubeck. And that's not scheduled until like next year. When next year? I don't know, maybe mid next year. Haven't sort of narrowed that quite yet down. But it's of course possible that trusted parties or people we know or enterprise partners or that kind of parties can join in earlier, or there can be test nets where people can run nodes, even if not the sort of production network. So those things will happen earlier. There are still a couple of obstacles to getting to that point, which need to be solved, but we're currently working on those ones. Those include like basically having this robust support for end-to-end encryption and the key exchange mechanisms implemented in the main libraries, which we have for JS and Java, as well as starting to use the WebRTC protocols instead of WebSockets, because when people run nodes on their machines, they're going to be behind firewalls and nets and that kind of stuff, and it makes the peer-to-peer traffic a bit tricky. But on WebRTC, it's sort of part of the protocol on how to do the tricks to enable that to work. So that's one aspect that needs to happen before we can actually like realistically allow people to join and run nodes in the network.
And one more question from Remy. Would people be able to run a node on a laptop, for example, or is it a constant connection requirement?
Yeah, I mean, since we're dealing with real-time data, then uptime and a persistent connection is definitely a useful thing to have. So from a sort of hardware requirements point of view, yes, you could run it on a laptop. It will probably run on a much smaller device as well, like a Raspberry Pi or whatnot. But you know, you'd probably want to have it like in an always on kind of setting. If you have nodes that come and go, it still works. Then you'd be sort of cut off from the data streams. And if there's incentive layers, then you wouldn't be earning money during those times that the node is offline.
Cool. All right. I think that's it. Thank you everyone for joining us. Thank you to the panelists. Thank you, María Paula, for moderating, and thanks, Henri, for the presentation. Yeah, I hope you all really enjoyed this. We're also going to put this online, so if you only saw half of this or had to leave earlier, then you can check that later on YouTube. And yeah, wherever in the world you might be, have a nice day and hope to see you all soon again.